Remember, the objective of any bond migration is always to find or form a more stable carbocation. If a more stable carbocation is not formed or a more stable compound is not formed during bond migration, the bond migration will not occur. So welcome back to our 5th class, and today's topic will be alkenes. Now, alkenes are of the most important chapter from hydrocarbons part. So this class will be a little bit longer and we will discuss 10 important questions from alkenes chapter. And our prime focus will be on ring expansion or bond migration, as these are the most trickiest and most important part in this year's joint examination. So let's start. Now the first question is very simple. It has been asked that if we react this compound with a bromine and CCl4, the product will be Y and Z, while Y is optically not active. That means Y is optically inactive, and we need to find the structure of Y. So first of all, the addition of bromine is always anti. So if there is this type of double bond and bromine gets added, so one bromine will get added from this position and another bromine will add from this position, and vice versa. So in this case, in this 2 point, one bromine will add to both the atoms will be added from anti-position. So in the first compound, look, you can see that both the bromine has been added from same direction. So this is obviously not the answer. And in option D and option E, there is only one bromine added. But in this reagent, that is when bromine is used with CCl4 solution, then 2 bromine must get added. So these 2 will always not be the answer, and this 2 is the probable answer. So let's find out which one will be the correct answer. Now this bromine gets added from the above position and this bromine added from the below position, and in this case this bromine added from the below and this bromine added from the above. Now if Y is to be optically inactive, it must possess a plane of symmetry. That means a mirror plane or a sigma plane. So in this compound there is no sigma plane. We can clearly see that if we try to draw a sigma plane like this bromine is above the plane and this bromine is below the plane, and hence the sigma plane will not hold. But in this compound, if we try to draw a sigma plane like this bromine and this bromine are both below the plane, and this compound possesses a sigma plane. So option C will be the answer. And we can clearly see that if option C is the Y and option Z will be the B, but it has not been asked in the question, so C will be our only option. Coming to the next problem. Now this problem is the example of a bond migration or ring expansion part. Now how can we say that it will form a ring expansion? Well, let's discuss. This compound looks like this. Due to the H plus, this bond will go on and catch a H plus, forming a positive charge on that carbon, and it will look somewhat like that. Now this bond will move on here and the positive charge will form here. So it will kind of look like this. Positive charge on this one. Now this bond will move here, making this carbon positive, as this bond or this carbon or this two is 2 degree, and if this bond moves from this position to this position, this carbon or this carbocation will be 3 degrees. So this will be much more favorable. So it will look like somewhat this. Sorry, this will all be a OH. My mistake. Anyway, so this will be like that, and carbocation will be formed in that carbon. Now how can we check that I have written that this ring perfectly? So number the carbon. This is 1, this is 2, this is 3, this is 4, this is 5, and this will be 6. So there will be a bond between 5 and 6, and the bond between 1 and 5 will break. So it is 1, 2, 3, 4, 5 and 6. So there is no bond between 1 and 5, and 6 and 5 bond has been formed. Now that carbon, that is number 6 carbon, there is a hydrogen which will remove to give our aromaticity in the ring. And why aromaticity? Because being an aromatic ring, it will give the compound an extra stability, and hence this aromaticity will form, and this is the final compound that we can get. So let's check which of the option is correct. Obviously not C and D, and in this case the OH is just adjacent to the ring junction, but here there is one extra carbon between the OH and the ring junction, and hence B will be our answer. Okay, now come to the third problem. It is clear, it is also evident that this is a 4-member ring and this is a 5-member ring, so obviously it is also a ring expansion like we have done previously. So it is asked a little bit of differently, that how many transition state and how many intermediate will form while this compound gets transformed into this one. So we just have to do the mechanism and find out the number of intermediates, and just remember the number of transition state is always number of intermediate plus 1. Okay, so we find out the number of intermediates and we find out the number of transitions from this formula, and our answer is well find out. So first what happened, this bond will go on and take up a H plus. Obviously the plus charge will form on this position, as this position is more substituted and more stable than this one. So this will be an H and a plus charge will be like this. Now this bond gets to that position. This is a 2 degree carbocation, and if the plus charge moves to this position due to this bond migration, and this will be a 3 degree, hence the bond migration is preferable. Remember, the objective of any bond migration is always to find or form a more stable carbocation. If a more stable carbocation is not formed, or a more stable compound is not formed during bond migration, the bond migration will not occur. So this will be 1, 2, 3, 4, 5. So a 5-member ring. Our 5-member ring is done. In number 1 there is hydrogen, and in number 2 carbon there is another methyl group, and the plus charge will form on the plus position. So this is the one. So this is our first intermediate. This is our second intermediate. Now the water will attack the carbocation and will form another intermediate, OH2 plus, like this. From this intermediate, H plus will be removed to form OH and H. Hence this is our third intermediate. So we have found out that number of intermediates is 3, and hence number of transition state will be 4 according to this formula, and only B matches our answer, and hence B will be the answer. So this is how a bond migration or a ring expansion occurs. Now next problem. This is looks scary due to this type of compound, but this is basically a very simple question. We have given osmium tetroxide, and the osmium tetroxide generally does what? It does syn dihydroxylation. That means In a double bond, if we attack with osmium tetroxide, two OH will attack and they will form or attack from the same side. So in this curve, so either they can attack from this side or they can get attacked from above side. So there is always two possibilities, and hence which has been asked how many products will be formed. Now, obviously our answer will be option 2, that once the wedge will attack from this side of plane and another time this will attack from below the plane. This is a very simple question. This compound is just here for to make look scary, nothing else. So the fifth question for today. Now, what does MCPBA does to a double bond or an olefinic bond? MCPBA we know are organic peroxide, and when an organic peroxide is added to any double bond, a 3-member epoxide ring or is formed. This is a very basic reactions, but how these reactions occur? Peroxide looks like somewhat this. And this oxygen is most electron deficient, and hence this will attack this oxygen. But so in this reaction, the double bond occurs as nucleophile and the peroxide occurs as electrophile. So more nucleophilic double bond or more electron rich double bond will preferably form the epoxide ring. And in this compound, we can clearly see that this double bond is more electron rich due to the presence of these two methyl group, and hence this double bond will preferably form the epoxide. So the answer will be clearly option D. It's very simple. We just need to know that the more nucleophilic double bond or more electron rich double bond will form the epoxide, and the question will be done. It is not much of tough questions for any JEE experience. So moving on to the next one. So here is the question number 6 for us. Now this question is particularly very easy. It is asked that which of this compound will react with H2PT more efficiently, or the rate of reaction for which of the compounds will be higher. So it is very clear that there is a steric interaction. As the double bond falls on this side, the hydrogen obviously will come from this side in both the cases. So in this case, in compound B, the CH3 is on the double bond side. So the hydrogen, when come from the double bond side, will have a steric interaction with CH3. But in this case, the CH3 is on the opposite side, hence there is no steric interaction. So obviously A will react faster. So A will be our correct answer. It is a very simple question, but sometimes people or students tends to overthink it, so they make the wrong choices. So come to the next question, question number 7. This is basically very basic question. It has been asked that we need to react a hydroboration oxidation reaction, complete and very simple reactions. But so what happens in a hydroboration and oxidation reaction? In a double bond, H and OH is added. So H is added to more substituted carbon and OH is added to the less substituted carbon. That means anti-Markovnikov of addition occurs. So this is the result of a Markovnikov addition, not anti-Markovnikov. So this is not the answer. And also after the reaction, there will be no presence of double bond. So this will also not be the answer. Now in these two cases, the addition of water is of anti-Markovnikov rule. So out of these two, one will be the answer. But which one will be the answer. Now if you think it like this, there is the double bond. If we write it like this, the boron, what happens, the BH2 and hydrogen added from the same side. Actually the boron will attack this side, hydrogen will add to this side, but what happens, the borohydride and the hydrogen both get added from the same side. That means a syn addition, and this is the stoichiochemistry of the reaction. That means the water the hydrogen and the hydroxy group will get added to the double bond from the same side. So you can see the CH3 is already present, but there is no hydrogen, so this hydrogen and this OH is added. But in case of A, the hydrogen and the OH is from opposite side, but in D, the hydrogen and the OH gets added from the same side. So in this case it is a syn addition, and we have already discussed that during syn addition or during hydrobolation oxidation, syn addition occurs. So D will be our correct answer. So why? Because during hydrobolation oxidation reaction, syn addition occurs. We have to keep that in mind. We all know how the reaction occurs, but we must know that the reaction is a syn addition. That is, both the groups attached in the same side. Now on the next problem, this is also an example of a ring expansion. What happens basically? It's a very simple reaction. So like if this is the ring, this C double bond CH2 CH3. Now this bond gets and attacks the H plus. Now this will look somewhat like that. C CH3 CH2 H, and this is the carbocation. Now we all know that 4-member rings are not stable compared to a 5-member or a 6-member ring. So this bond will open up and migrate to this carbon. Similarly, what we have already discussed, that when we are performing a ring expansion, we will number the carbons. So this will be 1, 2, 3, 4, 5. And if the bond between 2 and 5 breaks and gets attacked to the number 1 carbon, so there will be a bond between 1 and 5, and the bond between 2 and 5 will be broken. So it will be kind of look like that. If we draw a 5-member ring, this will be 1, 2, 3, 4, 5. So there is a bond between 1 and 5, and carbon number 2 will have the positive charge, and there is a CH3 group and another CH3 group on carbon 1. So this is the CH3 group and this is another CH3 group. Now what will happen? This carbon is a 2-degree carbocation, and from this carbon, this methyl will migrate to make the carbocation a 3-degree one. So the carbocation will get shift towards the carbon number 1. Now the bromine will attack this carbon and the compound will be formed like this: CH3, Br and CH3. So this is the compound that we have, and the answer will be option A. This is the only compound. Now most of the people will, most of the people will do, they will expand the ring. They will make a 5-member ring and they will attack the bromine on this carbon 2. Then they will form a compound B, but this is the wrong answer, because as This is a 2-degree carbocation and this is a 3-degree carbocation, and 3-degree carbocation is always more stable. Hence, after the degree expansion, there will be a migration of methyl group, and if you miss this step, you will get the wrong answer. So you have to keep this in mind, the stability of the carbocation. Okay, so the next question. Now this question is also involved a ring expansion. As you can clearly see that this is a 5-member ring and all the answers given are 6 members. So obviously there is migration. So how things occurred in this reaction? Basically, what happened, the H plus attacks this OH group. Now this O and this O will attack the H plus and it will remove as water. So after the water removal, we will get a compound like this. This is a carbocation, and for obvious reason, this bond will migrate here, forming a 6-member ring like this. And the plus charge will be here, as if we can number it like this: 1, it is 2, it is 3, 4, 5 and 6. So 3, there will be a bond between 3 and 1, and also 2 and 1. So this will be 6, this will be 2, this will be 1, 3, 4, 5, like this, and this will have the positive cation. But why this bond moves? Why this bond does not move? Because this carbocation is stabilized by the resonance of the oxygen atom, or the lone pair donation from the oxygen atom. So this 2-3 bond will move. Now there is a hydrogen in one, this will gets removed, and we will get a compound like this. Again, on the second step, H plus ROH is given. So on addition of H plus, this group, this position will also give rise to a carbocation, as this carbocation is stabilized by resonance. Next, ROH, that means this will attack the carbocation and will form a compound like this, R. Now we can obviously attack the ROH from here, but this is not the case because this is A actually. This A, we have to form A, and if we attack ROH on this carbon, the A will not form. So this is actually A and this is actually B. Now if they have asked us that what will be the structure of A, we must form this compound. So we went through these two intermediates are same in nature, but we must form this compound A after or before attacking ROH. So basically, which is the correct answer now? B is the correct answer, as we can see. And A is that this compound is A. Now we have saved the last or the most trickiest problem for the last. So what will happen? This is not a normal ozonolysis reaction. The H2O2 is given. That means we have already know that if the carbonyl or CHO group is formed, this CHO gets oxidized by H2O2 to CO2H group. Hence, this bond, what happens in ozonolysis? The double bond breaks and form a carbonyl compound, and on H2O2 addition, this carbonyl compound will form a COOH group. So in this case, this bond will break two carbonyl compound will form, and those two carbonyl compound will convert to carboxylic acids. So how it will look like? It will look somewhat like this. This OH, CH, OH, COOH, we have 8 membered ring. So this is 1, 2, 3, 4, 5, 6, 7, 8. So this is the 8 member ring. Now what will happen is there is all the compounds have the 5 member ring except this 6 member ring, but in this case this has been written that water will get eliminated. But if we try to eliminate a water from somewhat from these areas, only a 5 member ring can be formed like this. This OH and this OH. From these two OH, one water will be released. So how it will look like? Let's erase these numbers for our ease. Now this is the bond. So this is 1, this is 2, this is 3, this is 4, and one of the O atom will be present here. So this will be 5, a 5 member ring, and it will obviously it will be a lactam type of compound. So it will be kind of like that. So this is the 1, 1, 2, or we can say 1, 2, 3, 4, 5. Now from 3 we had a CH2OH. So from 3 we had a CH2OH, and from 2 we had a 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. That means 5 CH2 groups, then a CO2H. So this is the structure, and let's see which one is the correct answer. This will be not best because this is only OH. This is a 4, this is the not answer, and this one is the correct answer. So basically this problem is not much of tricky, but what makes the problem tough is this strange arrangement. So these are all the problems that may come from Alkenes chapter, and in this year, as we have already discussed, the bond migration is of very importance. So practice this bond migration part or ring expansion part very carefully. Okay, thank you students for watching, and all the best for examination. Thank you.